Dear ladies and gentlemen, welcome to my presentation, Quantification of a New Class of Retrofitting Systems and Standardization Approach. And this presentation is held by myself, Bernhard Valendi, and I also want to mention my co-author, Andreas Fecke. We are both structural engineers at SMP Ingenieure im Bauwesen. It's an engineering office in Karlsruhe, Germany, and we are specialized in earthquake engineering and structural dynamics. Okay, let's start with the presentation. Just a very short introduction. My name is Bernhard Valendi. I'm a structural engineer at SMP Ingenieure im Bauwesen GmbH. And I graduated at Karlsruhe Institute of Technology, KIT, in 2010. And I finished my doctorate. I did a PhD at KIT Institute of Reinforced Concrete Structures, and the topic was about retrofitting systems for masonry. And additionally, I have a couple of years working experience in structural engineering offices, both in Stuttgart, Germany, and Karlsruhe. And my special interests are concerning dynamic analysis and material testing. And the presentation I'm going to hold here is mainly about tests I've been conducting during my doctorate at the KIT Institute of Reinforced Concrete Structures, and it is about retrofitting systems for masonry. Just a quick look at the overview, and let's start with the introduction. I want to start to present the basic idea how retrofitting of masonry actually is working. And I limit myself to retrofitting of masonry with fiber reinforced polymers. You can see here, this picture shows masonry stones and plastered from both sides. And if you want to apply fiber reinforced polymer, you, in the first step with standard systems using epoxy glue, you have to remove the plaster as it is shown right now. Then you have to apply the glue, which is in most cases an epoxy glue, and afterwards you apply the actual textile system, which is mainly carbon fiber or glass fiber. And especially for non-load bearing walls, this masonry endures out of plane loading or bending load, and the fiber reinforced polymer stripes during the load situation have to endure tensile force, which is shown here. And during this load situation, there is bond stress transferred between the fiber reinforced polymer and the masonry itself. And the standard failure mode is brittle cohesive failure within the masonry stone. This is the standard failure mode for epoxy-based systems. And here is a photo shown from the PhD thesis of Uwe Pfeiffer from Kassel. And this cohesive failure is shown again. And as you can see here, there's a fiber reinforced polymer glued on a masonry stone, and the first a very thin layer of masonry stone, let's say something about 1 centimeter thick, is cracked and separates from the masonry stone. This is the standard failure mode for fiber reinforced polymers if you use standard glue, which is in most cases very stiff epoxy glue. The retrofitting system I want to introduce within this presentation, and which has been developed at the Institute of Reinforced Concrete Structures, and is called the seismic wallpaper. And the seismic wallpaper differs strongly from commonly used fiber-reinforced polymer retrofitting systems, as it is applied directly on the plaster. And you don't use stripes, you apply the full surface. And the main distinguishing feature of the seismic wallpaper are the mechanical properties of the glue, which is shown here. Polyurethane dispersion is used, and there is an elastic modulus of around 6 to 9 Newton per square millimeter. This is a very, very soft glue, and it behaves like it's almost like an elastomere-like behavior. And also quite important point to mention is that the glass transition temperature is below 0 degrees Celsius. And this is really distinguishing from epoxy systems which have glass transition temperatures something between 50 or 80 degrees Celsius. So this glue is used above its glass transition temperature, and this is the main feature of the system. And I want to show you why this special material properties of the glue are so important to the system. Despite the very, let's say, exotic material properties of the glue, the system itself works. And to prove this, I want to show you a short video from out-of-plane shake table tests which have been conducted in Skopje, Macedonia. And as you can see, here are two walls which are simultaneously excited. One wall, the right wall, there is no retrofitting system, and the left wall, there is the retrofitting system. Let's have a look. Let's have a quick look at the basic principles. Why do actually soft glues behave so well for masonry systems? That's because of, we remember the standard failure mode is a cohesive and a very brittle failure mode, which is governed by the tensile strength of the masonry stone. And the key in order to improve the mechanical properties of the applied textile retrofitting systems is to reduce maximum shear stress peaks which are transferred between the textile retrofitting system and the masonry block. Now let's analyze the distributed shear stress along a fiber reinforced polymer under an applied load which is indicated with F. And we have a look at two configurations, one soft glue configuration and a stiff glue configuration. And for the same load, you can see here the maximum shear stress peaks can significantly be reduced by the use of a soft glue. And it's like the weakest chain within the mechanical system due to the brittle cohesive failure mode could be fixed, let's put it like this, by the use of a soft glue. So these are the basics, the main working principles of the seismic wallpaper, but I also want to mention there's a huge field of applications for the seismic wallpaper. Especially, it has been developed especially for indoor walls, non-load bearing indoor walls, which mainly endure an out-of-plane or a bending loading during an earthquake situation. And as it is shown on these pictures here, after the Italian earthquake in L'Aquila in 2009, there is severe damage, especially for non-load bearing walls. And this topic is quite neglected in the current generation of European regulations. And yeah, I have to stress that the seismic wallpaper can offer here, in this case of application, a very elegant and safe intervention option. There are some regulations on national level in Europe how to quantify the reinforcing effect of fiber reinforced polymers for masonry. One of the most prominent ones is the Italian regulation CNRDT, and here the formula to quantify the maximum force which can be transferred to a fiber reinforced polymer before debonding starts is shown here on the upper left corner. And as you can see here, the maximum force is mainly a function of gamma, which means the fracture energy. And the fracture energy is mainly a function of the tensile strength of the masonry. As we remember, for epoxy-based systems, we have this very brittle cohesive failure. And for these systems, the national regulations work pretty well. But we remember, or we have a very different material behavior for the seismic wallpaper. And the standard failure mode for the seismic wallpaper is, as it is shown here, is not cohesive failure, it is an adhesive or a quasi-adhesive failure. Here, as it is shown in the down left corner, the load carry substrate and retrofitting system, the seismic wallpaper. You can see here there was a decoupling and it was an adhesive decoupling. And that is why the formulas provided in most regulations cannot be used for the quantification of the seismic wallpaper, as we don't have this brittle cohesive failure, and that's why the formulas for the quantification of the fracture energy cannot be used. So an alternative approach has to be it has to be worked on an alternative approach, and I want to introduce this approach. This is the most important test setup which has been used for the quantification of the seismic wallpaper. It is a single shear test with very short anchorage lengths, and this test setup was pretty easy to install, and many tests could be conducted in order to quantify the effects of testing speed, different carrier substrates, or the effect of air humidity or temperature. And if you are interested in the details from this test setup and why it is actually possible with this test setup to directly determine the so-called bond-slip relations, I recommend to have a look at my PhD thesis. These are the main outcomes from the test setup, which has been shown on the slide before. These are the so-called bond-slip relations or shear stress-slip relations. As you can see here, the maximum shear stretch with shear stress which is transferred is around 0.5 to 0.7 Newton per square millimeter, and decoupling takes place at around a slip of 1 to 1.5 millimeter. If you are familiar with bond-slip relations for epoxy-based systems, the very soft behavior of the glue can also be seen here. And the most important thing about these bond-slip relations is, of course, to get the fracture energy, which is the integral of the curve. And in this case, let me show the next slide. It's indicated like here. Yeah, let's take test number 4 as reference, and the gray surface is the fracture energy. Another test setup which is also used for the quantification of the seismic wallpaper is here a single shear test, and in this case anchoraging lengths of until 800 millimeters could be realized, and with this test setup, also the cyclic behavior of the retrofitting systems has been examined. I just want to mention that we also used fiber optical sensors in order to analyze the shear stress distribution, but yeah, that's a little bit too much for this presentation. Let's have a look at the results of a typical cyclic loaded test. This is a typical result from a cyclic loaded test. And as it is indicated here, we see the so-called global slip. That is the displacement at the beginning of the anchorage length and the force. And there are actually two things which I would like to stress. The first is we have very, very, very large displacements until actually decoupling or failure takes place. Something between 5 to 7 millimeters displacements until failure of the system occurs. That's the first point. And the second point is, as you can see here, we have very, very narrow hysteresis. And this is typically for fiber reinforced polymers, and this is completely different to reinforced concrete with steel, for example. And this has severe consequences in terms of ductility of the systems. But this is something I want to analyze or get back during a slide where I want to introduce some numerical parameter studies which have been conducted in order to analyze this aspect of the very narrow hysteresis. There are a lot of numerical studies which have been conducted during the quantification of the seismic wallpaper. A lot of finite element models analyzing the behavior on component level, but also some equation solvers which have been implemented in MATLAB. And I would like to introduce the results from an equation solver which simplifies the retrofitted masonry to a single degree of freedom system. And the basic idea is to simplify the masonry under the assumption that there is one central crack forming in the center of a wall, and the material behavior which is implemented links the crack opening to a transferred tensile force within the retrofitting system. And for this material behavior, an ideal linear elastic plastic material behavior is implemented, but we have a complete damaged system, which means after reaching the plastic plateau, there is no additional energy dissipation, which means we have completely closed hysteresis. And with this material implementation, the dynamic equilibrium, which has been shown here on the bottom right corner of the slide, the equation is solved numerically in MATLAB. And this equation solver has been implemented in order to check the effect of additional gain of maximum global slip and its effect on the retrofitting effect of the system. So the question is, if we allow actually larger global slips, is there an additional gain of load-bearing capacity? So let's have a look at the results. I analyzed two settings. One setting is decoupling or failure of the system occurs at 4 mm global slip, and the other setting is increase of global slip of 100%. So failure of the system occurs at 8 mm global slip. And let's compare the maximum load-bearing factor for the two settings. Load-bearing factor is something I defined by myself. If you are very interested in what it means, let's have a look at my PhD thesis, but it is shortly spoken, it means load-bearing factor is a comparison between the load which can be transferred from doing a dynamic analysis in comparison to a quasi-static analysis. So let's have a closer look. And as you can see here, from setting 1 to setting 2, we have an increase of load-bearing capacity from 1.14 to 1.19. And this is astonishing. For me, it was astonishing. It's not too much. And even though we increased the maximum global slip around 100%, the increase of load-bearing capacity is by far not in the same range. And this is a very strong indicator that the very closed form of the hysteresis strongly affect the behavior of the seismic wallpaper, of course, and the seismic wallpaper, although it is really useful and has a lot of advantages, but cannot be compared to, let's say, reinforced concrete systems with steel bars in terms of ductility. It's not comparable. So how can these results actually be used in order to have a quantification concept on component level? Let's have a look at the Italian regulation. And there is an analogy used for masonry beams, which are retrofitted with fiber reinforced polymers. And it is actually considered like reinforced concrete bending beam. And so we have somewhere, let's say, a crack within the masonry, and the tensile force is transferred to the fiber reinforced polymer. We have an inner arm of lever, and there's a compression zone within the masonry. And if you know the capacity or the bending capacity or the compression capacity of the masonry, and if you know the tensile force of the retrofitting system before decoupling takes place, the moment of resistance on the component level can actually quite easy be determined. As the seismic wallpaper is applied on the complete surface of a masonry component, and as the shake table tests have proven the very homogeneous behavior of the retrofitted masonry itself, I would like to suggest a standardization or quantification concept of masonry retrofitted with a seismic wallpaper on component level according to Eurocode 6 regulations. These simplified regulations deal with out of plane loaded masonry walls under wind load, and there the load-bearing capacity is directly linked to tensile strength of the masonry. And I would like to suggest that the retrofitted cross-section of a masonry beam can actually be homogenized and an equivalent tensile strength of the masonry cross-section by using the seismic wallpaper can directly be used, and these diagrams, as it's shown here, can be used for the dimensioning or for the proof of safety of, let's say, dynamically or earthquake loaded walls. Before I finish my presentation, I would also like to mention an additional field of application for the seismic wallpaper. This is a very short outlook, and it is from a project we are doing for a client within our engineering office. And this is retrofitting of historical masonry facades against blast loads. And this also leads to an out-of-plane loading of the masonry itself, and is a very interesting case of application for the seismic wallpaper as well. And we are actually right now evaluating if the seismic wallpaper can be used for our client's problem.